Today I want to talk about resonance structures. Right. Resonance structures look like they're about the location of double bonds, but they're really, in some ways, about the imperfections of Lewis dot structures. If we have a molecule with a double bond, and here my example is going to be SO2. Okay. Now you can't tell the SO2 has a double bond until we draw the structure, but if we draw this, we can tell that we have 6 plus 2 times 6 equals 18 valence electrons. If we run quickly through this, we put sulfur in the middle, we draw oxygen on the outside, and we fill in our octets. If we do this, you will see that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. We only have 18 valence electrons to actually play with, which means that's 2 electrons too many, which means that we need 1 extra bond. So the question is, where does the extra bond go? So, well, we could draw it on the left. We could have something like this. O, double bond S. Extra pair of electrons. Fill in our octets. Right, top and bottom. Or we could have this. Right, so we have, right, the bond could be in either of 2 places, right? Well, the answer is really, it's not so much that it could be here or here. It really is both places, right? It's really both places at the same time, right? There's not a good way of representing this with Lewis dot structures. With Lewis dot structures, we have to put dots or bonds in specific places. But what we really want is something that looks like this, where we have the O and the O with a single bond, and then we have that extra pair of electrons smeared across both locations, right? Right? As if we had like 2 1.5 bonds. Right? It's almost like we had 2 1.5 bonds instead of a single and a double. Okay? And a way we can test this is if we had something like this, S double bond O, and single bond O, this would have more attraction between, right? Because it's more electrons shared by the 2 atoms. This would be more attraction, and so it would have 2 characteristics that are important. It would be stronger, and it would be shorter. Right? If we were to look at this bond, this is less attraction. It would be weaker and longer. Right? If there's less attraction between the atoms, they're going to be spread farther apart. Well, it turns out that we actually have something like this. As I said before, it's like smeared, where these are equally strong and equally long. Well, that rhymes. It's kind of cool. Look at that, I'm like a poet. All right, so equally, right? And so if we actually like froze SO2 and we ran X-rays through it so that we could measure the crystal structure and figure out the length of every bond, we would find that they are all equal bonds. So we don't have this picture. We have something like this. Well, how do we do it with Lewis dot structures? And you're like, I'll draw dotted lines, Mr. Safford. That won't be a problem. Well, that's not how we do it. So instead, what we're going to do is we're going to do what we call resonance structures. We're not going to draw just one. We'll draw both. So we'll draw this, and we'll draw all the extra electrons. And we will draw this. And you'll say, I'll never finish a structure. This will take forever. Yeah, maybe. But maybe not. I mean, I'm already done now. And what we draw is a double-headed arrow between them, and we draw both of them. And we say that this is two what are called resonance structures. Right, two resonance structures representing one molecule. Okay, and it's an important idea that this is not two different molecules. This is one molecule. It's just two what we call resonance structures, as if the bond was bouncing back and forth between the two, resonating as it were, and the two bonds are exactly equal, right, because they represent half of the overall structure. Okay, so the overall structure is the average of the resonance structures. And that's pretty much it. So if you have multiple places to put an extra bond, right, that are all equivalent, we instead draw resonance structures. So let's practice this kind of quickly. In your notes, there is an ion, CO3 2 minus. Right? CO3 2 minus has, let's see, 4 plus 3 times 6 plus 2, right? The charge, -2, the 3 oxygens, and the carbon, right? For a total of 4 plus 18 is 22, plus 2 is 24 electrons. If we draw our skeleton, we have carbon in the middle, oxygens on the outside, oxygen on the outside, oxygen on the outside. Okay, dot, 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 dot. Right? And we have drawn 26 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons. All right. Well, we know that we need one extra bond. Okay. Because 26 minus 24, we need one extra bond. Well, we now have 3 equivalent places. And so this is going to need, we're going to require 3 resonance structures. And you'll simply draw the bond in all 3 places. So if I lay it out quickly, here's my oxygens in all 3 places. Draw my double-headed arrows, and I can simply put the double bond here, here, or here. Then I just simply fill in my dots. Right? Notice that this is a full set of octets, 2, 4, 6, 8. The carbon has a full octet, 2, 4, 6, 8. Right? And this oxygen also has a full octet, 2, 4, 6, 8. So I can just copy that pattern over and put 4 electrons on each oxygen with a double bond and 6 electrons on each oxygen with no double bond. Okay, and so this, oops, forgot these guys, right, would be my picture for carbonate ion. It would be all 3 of these together, okay, which is cool, right? So we have 3 equivalent bonds. It would be like 3, in this case, like 1 1/3 bonds, if you will, in terms of bond strength, right? So it's 3 exactly equal bonds, not 1 double and 2 single, right? That's what we're representing here. Now, to throw back to an earlier class, let's take a look at this for a second. If we have a CO3 minus like this, or an earlier topic, if we wanted to assess formal charge, and we should always consider this, right? This carbon has 4 bonds, right? But carbon takes 4 bonds, so that's a formal charge of 0. This oxygen has 2 bonds, but oxygen takes 2 bonds normally, so that's a charge of 0. But this oxygen has 1 too few bonds, and so it has only 1 bond instead of 2. And so this guy is going to have a negative charge, right? And we can do that because it'll be 6 minus half of 2, right? And you can actually do the calculations. So this oxygen will also have a formal charge of -1. And if we look at it, the overall charge on carbonate ion is going to be 2 times -1 or -2, which is what we would predict from this structure. So yeah, formal charge, it still applies. Okay. In fact, if I'd gone back to this sulfate, sulfur dioxide, I apologize, not sulfate, sulfur dioxide, right, we would see that this guy has 3 bonds instead of 2, right? It's 3 bonds instead of 2, and so that would give it a +1 charge. This one has 1 bond instead of 2. Right? And so it would have a -1 charge, right? Notice that -1 plus 1 adds up to 0, and the overall structure charge on SO2 is 0. Okay, so yay, formal charge. All right.